In the previous two lectures, we have laid the foundation of sets and function. We have introduced set theory, the naive set theory, and different operations such that union, intersection, and complements, and discussed their properties. Uh, then we move on and introduced functions, and in function we have get the idea of what the function is, and we also discussed different types of functions like one-to-one function or onto function or bijective functions, uh, like that. We have also introduced the idea of inverse mapping, and given a mapping, how to get the inverse. We have also discussed that thing, and we have discussed several properties of this inverse function, and finally we give the idea of multiplication of mapping, how to multiply two given function or mapping, and lastly we have discussed few given some example of some weird function which you can or you may have encountered in different branches of mathematics. So now today's our discussion will discuss more about this set and functions. Basically, we will concentrate today on product of sets. We will introduce Cartesian product, and also we will introduce what is relation, uh, this thing, and also I will discuss equivalence relation. We will then go on and discuss uh, some important theorem regarding this equivalence relation. So okay, so let's start from very basic, the real line. So we shall often have occasion to weld together the sets of a given class into a single new set called their product, or you can say Cartesian product. The ancestor of this concept is the coordinate plane of analytic geometry. The coordinate plane of analytic geometry. That is, a plane equipped with usual rectangular coordinate system. Okay, so we have a plane and we have a rectangular coordinate system associated with that thing. Okay, so we will give a brief description of this fundamental idea uh, with a view to pave the way for our discussion of products of sets in general. So first, a few preliminary comments about real line. We have already used this term several times without any explanation, and of course, what we mean by it is an ordinary geometric straight line whose points have been identified with or coordinatized by the R, capital R, of all real numbers. Okay, so we mean actually by real line mean an ordinary geometric straight line whose points have been identified with or coordinatized by the set R, capital R, of all real numbers. We generally use the letter capital R to denote the real line as well as the set of all real numbers. Okay, so the letter capital R is used to denote the real line as well as the set of all real numbers. And we often speak of real numbers as if they are points on the real line. So I'm again repeating that we often speak of real numbers as if they were points on the real line, and of points on the real line as if they were real numbers. So both way. So we consider or often speak of real numbers as if they were points on the real line, and the points on the real line as if they were real numbers. Let no one be deceived into thinking that the real line is a simple thing, for its structure is exceedingly intricate. Okay, we may come across some properties in near future, but I will assure, or I can assure, that its structure is exceedingly intricate. Our present view of it, however, is as naive and uncomplicated as the picture that you can see in the slide. So we have real line, and you can see some points in the figure, okay, in the slide. Okay, generally speaking, I assume that you have some familiarity with simple properties of the real line, those relating to inequalities. Okay, and basic algebraic operations of like such that addition, subtraction, multiplication, division, like that. One of the most significant facts about real number system is perhaps less well known. So what is it? This is the so-called least upper bound property. The least upper bound property is perhaps less well known about real number, which this real least upper bound property asserts that every non-empty set of real numbers which has an upper bound has a least upper bound. So I am repeating again. This least upper bound property says or asserts that every non-empty set of real numbers which has an upper bound has a least upper bound. So we have a set, non-empty set of real number. This is bounded above or it has upper bound. So this property states that if it has a upper bound, then it has a least upper bound. It is an easy consequence of this that every non-empty set of real numbers which has a lower bound has a greatest lower bound. Okay, so the reverse way, this property can be proved from the previous one, that is least upper bound property. The least upper bound property says every non-empty set of real number which is bounded above has a least upper bound, and the other way, every non-empty set of real number which is bounded below has a greatest lower bound. This property can be proved from the previous one. Okay. All these methods can be developed rigorously on the basis of a small number of axioms, and detailed treatment can be found in any book on elementary abstract algebra. Okay, so now to construct this, to construct the coordinate plane, we now proceed as follows. So we are going to construct coordinate plane. So how to construct this coordinate plane? We take two identical replicas of real line. We take two identical replicas of real line, which we'll call x-axis, and one we call x-axis and another we will call y-axis, and paste them on a plane at right angles to one another in such a way that they cross at the point 0, that is the 0 point on each. So we have a two line, one we call x-axis, another, that line or real line, we call y-axis. They both have the point 0. We put them on a plane perpendicularly such that 0 point on one line and 0 point on the other line coincide. Okay. The usual picture, the picture you can always see from the slide. It's very easy. Now let P, capital P, be any point in the plane. So we have a plane. We took two lines, two real lines. One we called x-axis and another y-axis. We put them one perpendicularly to each other, and they cross at 0. And we pick any point P with coordinate, or any point. First we pick any point P on the plane P. Now how to associate a coordinate with that point capital P? This is our task. We project. So how can we associate a coordinate with P, or how do we associate a coordinate with P? That we project P perpendicularly onto points Px and Py on the axis. So we project the point P perpendicularly on the axis. Now if small x and small y are the coordinates of Px and Py on their respective axis, this process leads us from the point P to the uniquely determined ordered pair x, y of real numbers. Okay, so we have a point P. We take a point P on the plane. We project that point on the axis. Okay, so from this projection we determine an ordered pair small x and small y of real numbers. So what is small x and what is small y? Small x and small y are called, or they are actually the projections, and they are called the x coordinate and y coordinate of P. Now we can reverse the process. We can reverse the process, and starting with the ordered pair of real numbers, we can recapture the point. So the process goes both ways. So we have a point on the plane, and we can associate a pair of real number with that point via the projection method. You can see, or you can follow from the picture. So we have a point P, we project it on x-axis. That projection is, we rename that as Px, the point, and another projection on y-axis, that is Py, which is equals to small y, and we associate that point x and y with the point P on the plane. So we have assigned two ordered real number with the point P, and conversely, if we have ordered real number, we can uniquely determine a point P on the plane. This is the manner in which we establish the familiar one-to-one correspondence between the point P in the plane and ordered pairs small x small y of real numbers. So we have a one-to-one correspondence between pair of real numbers and point on the plane. In fact, we think of a point in the plane and its corresponding ordered pair of real numbers, which is an algebraic object, as being to all intents and purpose identical with one another. So the point P and the ordered pair x, y, they are equivalent or identical with one another. The essence of analytical geometry lies in the possibility of exploiting this identification by using algebraic tools in geometric arguments and giving geometric interpretations to algebraic calculations. So that is the part of analytic geometry. In analytic geometry, we analyze the geometry via this coordinate system, or we do some algebra via this coordinate system we have introduced, and we give some conclusions or we do some calculations. Okay. The conventional attitude towards the coordinate plane in analytical geometry is that the geometry is the focus of interest, and algebra of ordered pairs is only a convenient tool. Okay. Here we reverse this point of view. For us, the coordinate plane is defined to the set of all ordered pairs x comma y of real numbers. Okay, so we can satisfy our desire for visual images by that using figure on the board, figure 2 as a picture on this set or of this set, and by calling such an ordered pair a point. But this geometric language is more convenience than a necessity. Okay. Our notation for the coordinate plane, the notation we use is r cross r, that is capital R cross capital R, or r square. This symbolism reflects the idea that coordinate plane is the result of multiplying together two replicas of the real line R. So we multiply two real number R and R and we get R square. This R square or this symbol R square is our coordinate plane. It is perhaps necessary to comment on one possible source of misunderstanding, which we may do, that we have to discuss. That is, when we speak of R2 as a plane, we do so only to establish an intuitive bond with our previous experience in analytical geometry. So, but our present attitude is that this R2 or R square is a pure set and has no structure whatsoever, because no structure has yet been assigned to it. Okay. So we remarked earlier that space is a set to which has been added some kind of algebraic or geometric structure. We shall convert the set R square into the space of analytical geometry, or we can do that by defining the distance between any 2 points x1 y1 and x2 y2 to be like that, root under x1 minus x2 whole square plus y minus y2 whole square. This is the concept of distance. So the notion of distance endows the set R square with a certain spatial character, which we shall recognize by calling the resulting space. There is an Euclidean plane. So we have R2, we associate the concept of distance like that, and this resulting space is called Euclidean plane instead of coordinate plane. Okay, we assume that you are fully acquainted with the way in which the set capital C of all complex numbers can be identified with the coordinate plane R square. If small z is a complex number and if small z has the standard form x plus iy, where x and y are real numbers, then we identify z with the ordered pair x comma y, and thus with an element of R2 or R square. So we have a complex number z. If this complex number z has the standard form x plus iy, where x and y are real numbers, then we identify z with the ordered pair x comma y, and thus with an element of R2, a correspondence. Okay, the complex number, however, are much more than merely a set. Is a much more richer property. Okay, they constitute a number system with operations of addition, multiplication, conjugation, like that. When the coordinate plane R square is thought of as consisting of complex numbers and is enriched by the algebraic structure it acquires in this way, it is called the complex plane. The letter capital C is used to denote either the set of all complex numbers or the complex plane. We shall make a space out of the complex plane in the later section. Now suppose capital X1 and capital X2 are any two non-empty sets. Capital X1, capital X2, any two non-empty sets. By analogy with our above discussion or the previous discussions in the previous slides, the product x1 cross x2 is defined to be the set of all ordered pairs small x1 comma small x2, where small x1 is in capital X1 and small x2 is from capital X2. So we have two sets, capital X1 and capital X2. We define the product x1 cross x2 is defined to be the set of all ordered pairs that we have to take in mind very carefully, that this is the collection of all ordered pairs x1 comma x2, where x1 is from capital X1, the small x1, the small x1 element is from capital X1, and the element x2 is from the set capital X2. In spite of the arbitrary nature of capital X1 and capital X2, their product can be represented by a picture. That picture we have drawn, okay, which is loosely similar to the usual picture of a coordinate plane. Okay, you can easily verify that picture. The term product is applied to this set, and it is thought of as a result of multiplying together the sets x1 and x2 for the following reason. If capital X1, the set capital X1 and the set capital X2 are finite sets with number of elements m and n respectively, that is, the set capital X1 has m elements, small m elements, and the set capital X2 has small n elements, then that is obvious that the set X1 cross X2 has m into n, that is mn elements. Now if is a mapping from x1 to x2 with domain x1 range in x2, its graph is that subset of x1 cross x2 which consists of all ordered pairs of the form x1 f of x1. So I'm again repeating, we have a set, or sorry, we have a function from x1 to x2. The f is a function from the set capital X1 to the set capital X2, where the set X1 is the domain of the function and the range lies in X2. Then the graph of the function, which we have discussed in our previous talk, the graph of the function is a subset of, or is that subset of x1 cross x2 which consists of all ordered pairs of the form, the ordered pair of the form x1 small x1 comma f of x1. So we observe that this is an appropriate generalization of the concept of the graph of a function, and as this occurs in elementary mathematics. This definition of the product of two sets extends easily to the case of n sets for any positive integer n. So we can take small x1, capital X1, capital X2 up to capital Xn. They're all non-empty sets, and their products capital X1 cross capital X2 cross up to capital Xn. They're all, this is the set of all ordered n tuples. What is the n tuple? X1 comma small x2 up to small xn. These ordered n tuples where each xi belongs to the set capital Xi for each I. Okay. Now, if this all xi's are same, that is, if this all xi's are all replica of a single set capital X, that is x1 is equals to x2 is equals to up to xn, they are all equal and they are all equal to capital X, then the product is generally denoted by the symbol x to the power n. Okay, these ideas specialize directly to yield the important sets Rn, capital R to the power n, and capital C to the power n, Cn. How? For basic information, the set R to the power 1 is nothing but R itself. That is the real line. R2 is the coordinate plane. R3, the set of all ordered triplets of real numbers, and is a set which underlies solid analytical geometry. And we assume that we are familiar with the manner in which this set arises. Though the introduction of rectangular coordinate system into ordinary three-dimensional space. We can draw pictures just as in the case of coordinate plane, and we can use geometric language as much as we please. But it must be understood that the mathematics of this set is the mathematics of order triples of real numbers, and that the picture are merely an aid to the intuition. Now, once we fully grasp this point of view, there is no difficulty whatsoever in advancing at once to the study of the set Rn of all ordered intuples of real numbers for any positive integer n. It is quite true that when n is greater than 3, it is no longer possible for us to draw the same kinds of intuitively rich picture, but at most this is merely an inconvenience. We can and we must continue to use suggestive geometric language. So all is not lost. The set C to the power n, capital C to the power n, is defined similarly. It is the set of all ordered intuples of complex numbers z1, z2, z up to zn of all complex numbers. Each of the set Rn and Cn plays a prominent part in our later discussions or the discussion of other later topics. We emphasized previously that for the present and coordinate plane, or for the present, the coordinate plane is to be considered as merely a set and not a space. So we just at present consider coordinate plane is merely a set, it's not a space. Similar remarks apply to Rn and Cn. In due course, we'll impart form and content to each of these sets by suitable definitions. We shall convert them into Euclidean and unitary n spaces which underlie and motivate us so many developments in modern pure mathematics, and we shall explore some aspects of their algebraic and topological structure to the last or part of our discussions in future. But as of now, this is the point we insist on. Neither one of these sets has any structure at all. As we doubtless suspects, it is not enough that we consider only products of finite class of sets. The needs of topology compel us to extend these ideas to arbitrary class of sets. So we need to, the situation of topology compels us to extend our ideas of this product to arbitrary class of sets. We define the product x1 cross x2 cross up to xn to be the set of all ordered intuples small x1 small x2 up to small xn, such that each small xi is in capital Xi for each subscript I. Now to see how to extend this definition, we reformulate it as follows. How we can extend this idea? So for that we need an index set. We have an index set capital I consisting of all integers of the form or integers from 1 to n, and corresponding to each index I small I, we have a non-empty set capital Xi. The n tuples small x1, small x2 up to small xn is simply a function defined on the index set capital I with the restriction that its value, that is small x of I, is equals to small xi as an element of the set capital Xi for each small I belongs to the index set capital I. Our point of view here is that the function x small x is completely determined by and is essentially equivalent to the array small x1, small x2 up to small xn of its values. So we have an index set I consisting of integers 1 to n, and corresponding to each index small I we have a non-empty set capital Xi. The n tuple x1, x2 up to xn is simply a function. It is simply a function. We can call it, or you can say, x. It is defined on the index set I with the restriction that its value x of I is equals to xi is an element of the set capital Xi for each I in capital I. Our point of view here is that the function x small x is completely determined by and is essentially equivalent to the array x1, x2, xn of its values. Now the way is now open for the definition of products in their full generality. So we can take xi be a non-empty class of non-empty sets indexed by the element small I of an index set capital I. So we have a non-empty class of non-empty sets. The sets xi need not be different from one another. Indeed, it may happen that they are all identical replicas of a single set. They are only distinguished only by their indices. So we have a class, non-empty class of non-empty sets xi. The product of the sets xi, we write P I belongs to I, capital I overall xi, and it is defined to be the set of all functions x small x defined on the index set I such that x of I is an element of the set capital Xi for each index I small I. We call the set capital Xi the ith coordinate set. When there is no misunderstanding or no confusion about the index set, that symbol P of xi, where I is belongs to the index set capital I, is often abbreviated to PIXI. The definition we have just given, this definition requires that each coordinate set be non-empty before the product can be defined or can be formed. It will be useful if we extend this definition slightly by agreeing that if any of the xi's are empty, then PIXI is also empty. Okay. So if any xi if any xi's are empty, pixi is also empty. This approach to the idea of products of a class of sets by means of function and defined on these functions defined on index set is very useful, mainly in giving the definition. In practice, it is much more convenient to use the subscript notation x subscript I instead of the function notation x of I. Okay, this is always convenient. Now we then interpret the product pixi as made up of elements x, each of which is specified by the exhibited array xi of its values in the respective coordinate sets capital Xi. We call small xi the ith coordinate of the element x, that is of xi. The mapping small pi of the product pixi onto its ith coordinate set xi, which is defined by pi of x is equals to xi. That is the mapping whose value at an arbitrary element of the product is the ith coordinate of the element is called the projection onto the ith coordinate set. So the mapping pi which takes xi to x, sorry, this the mapping pi which take x to xi is called the projection onto the ith coordinate set. The projection pi selects the ith coordinate of each element in its domain. That is clearly one projection for each element of the index set capital, and the set of all projections plays an important role in the general theory of topological spaces. So in the previous section, what we have discussed, we consider a non-empty set capital X, and we discussed the decompositions of capital X into non-empty subsets which fill it out and have no elements in common with one another. We have also give attentions to the tools which are normally used to generate such decomposition, such as the tools that we mean by actually is equivalence relations. So now partition, we are going to discuss what partition is. A partition of a set X is a disjoint class of sets capital Xi, they are all non-empty subsets of X, whose union is the full set X itself. So I am again repeating, by partition of a set capital X, we means a non-empty, some non-empty subsets Xi, that is, we can also say they are class of sets, class of non-empty sets, they are also disjoint, and their union is the full set X itself. These Xi's are called the partition sets. So they are creating these partitions. This can be expressed somewhat differently. A partition of a set X is a result of splitting it or subdividing it into non-empty subsets in which in a way that each element of X belongs to one and only one of the given subsets. So by mean partition, in another way we can see that by partition we means that we are splitting a set or subdividing a set, or uh, we are subdividing it into non-empty subsets in a way such that each element of the sets, each element should belong to one and only one of some given subsets. So for example, we are taking an example, we can take the set capital X as a set containing the integers 1, 2, 3, 4, 5. The 5 elements are there. We have given two ways of taking partition, where you can see we have given examples how to partition the set X in two ways. The number one, you can see the set is divided into the partitions 1, 3, 5, the set containing 1, 3, 5, and another set containing 2 and 4. This is one way. And another way, you can also see that this same set can be again partitioned like this: the set containing 1, 2, 3, and another set containing 4 and 5. There are two different partitions we have discussed. Now if X is the set of all real numbers R, we can partition X into set of all rationals and set of all irrationals. This is one way of partitioning. Or into you can also partition it like infinitely many closed open interval of the form n plus 1, where n is closed and n plus 1 is open, where n is closed and n plus 1 is open. This interval, this closed open interval, n is obviously an integer. We can take these infinitely many closed open intervals, and we can express the set of all real numbers, or we can partition the set of real numbers in these infinite ways. Now if X is the set of all points in the coordinate plane, then we can partition X in such a way that each partition set consists of all points with the same X coordinate, or each partition set consists of all points with the same Y coordinate. That means we can partition it by some means of some horizontal lines, that is whenever Y coordinate is fixed, or by some vertical lines, vertical strips, vertical lines, by when the coordinate X is fixed. Now other partitions of each of these sets will readily occur. You can always do it yourself. In general, there are many different ways in which any given set can be partitioned. These manufactured examples, the examples we have shown, are admittedly rather uninspiring and serve only to make our ideas more concrete. Later, we will consider some other examples which are more interesting to our present purpose. Now, we have introduced partition. Now, a binary relation. What is binary relation? A binary relation in a set capital X is a mathematical symbol or verbal phrase which we denote by capital R Okay, in this discussion, such that for each ordered pair x comma y of elements of x, the statement x or y is meaningful in the sense that it can be classified definitely as true or false. So the binary relation in a set X is a mathematical symbol or verbal phrase which you can denote by capital R in this here, and is defined such that for each ordered pair x comma y of elements of X, the statement x or y is meaningful in the sense that it can be classified definitely as true or false. For such a binary relation, x or y symbolizes the assertion that x is related to y by the relation R, or x is R related to y. And whenever we say x R not R, y, that is the negation thing. This says that x is not related to y by the relation R, or x is not R related to y. We write that symbol like that, x R cross y. So many examples of binary relations can be given, some familiar and other maybe less familiar. So some mathematical and other may not be mathematical. For instance, you can take this example, that if x is a set of all integers and R is interpreted as to mean is less than the relation is less than, which of course is usually denoted by the symbol less than, then we clearly have 4 less 8, or 5 not less 3, that is 4 is R related to 7 or 8, like that, and 5 is not R related to 3 or 4. We're speaking of binary relations, which are so named. They are named because they apply only to ordered pairs of elements rather than to ordered triples. Uh, Here we drop the qualifying adjective and speak simply of a relation in X. Now, since we shall have occasion to consider a relation of this kind. Now, we assume that a partition of our non-empty set X is given, and we associate with this partition a relation in X. This relation is defined in the following way. So we have a set X, and we assume that a partition of our non-empty set X is given, and we associate with this partition a relation in X. This relation X is defined in the following way. We say that X, small x, is equivalent to Y, small y, and we write this X wiggle Y if X and Y belong to the same partition set. So whenever X and Y belong to the same partition set, we write X is, or X wiggle Y. Now it is obvious that this relation has the following properties. What are those properties? Number one, X is, or X wiggle X for every X is evident. So this properties we call reflexivity. So an element X is self-connected, or X wiggle X is evident. the property number 2, if x will y, this implies y will x. This is a symmetric property. Is also very obvious. So that is, if x and y belongs to, or x equal y means x and y belongs to the same partition, so yx should be belongs to the same partition. This is a property, symmetry property. This property we call symmetry. And the third one, x wiggle y and y wiggle z. So x wiggle y, this means x and y belongs to the same partition. Y wiggle z, it means y and z belongs to same partition. Now since the partition are disjoint, so x, y, z, they all belongs to the same partition, and this means x and z belongs to the same partition, that is x will z. This property we call as transitivity property. This particular relation in X arose in special way in connection with a given partition of X, and its properties are immediate consequence of its definition. Any relation whatever in X which possesses these three properties is called an equivalence relation in X. So what we have learned? We have just seen or learned that each partition of X, it has associated with it a natural equivalence relation in X. So we have a partition, there is a corresponding equivalence relation. Now the question is, or the basic thing that we ask, that can we reverse this thing or reverse this situation? That is, if we have an equivalence relation, can we have a partition? And so we now reverse the situation and show that given equivalence relation in X, it determines a natural partition on capital X or of capital X. So we have shown that every partition induces an equivalent relation. Now we go backwards and we show that an equivalent relation will give a partition. So let wiggle be an equivalence relation in X. So we have an equivalence relation wiggle in X. That is, we assume that this relation, this wiggle, is reflexive, symmetric, and transitive in the sense we have described in the previous slide. Now, small x, if small x is an element of the set capital X, the subset of X defined by X or box X, we define as, we write in this way, that is a collection of all elements Y such that Y wiggle X. And this set is called the equivalence set of X. The equivalence set of X is the set of all elements which are equivalent to X. Equivalent means any element which is related to X. That is the collection of all Y such that Y will X. That is the Y or those elements that are related or wiggle related, y wiggle x, these all collection of elements, this collection of elements we call box X, and this set forms the partition of X, partition of all the set X, capital X. By reflexivity property, small x belongs to the class X for each element X in capital X. So each equivalence set is non-empty and their union is capital X. Now it remains to be shown that any two equivalence sets, that is the equivalence box x1 and box x2, they are either disjoint or identical. We prove this by showing that these equivalence sets x1, the class x1 and x2, they are not disjoint, then they must be identical. Suppose the equivalence class x1 and equivalence class x2, they are not disjoint. So what happens? That is, suppose they have a common element, say z. Now z belongs to both equivalence set, that is z wiggle x1 and z wiggle x2. So by symmetry we can also say that x1 wiggle z. Now if y be any element of the equivalent class x1, so that y wiggle x1. Now since y wiggle x1 and x1 wiggle z, transitivity follows, and from transitivity we can say that y wiggle z. By another application of transitivity, y wiggle z and z wiggle x2, this implies y wiggle x2, so that y is in equivalent class x2. Now y, what is the element y? Y was chosen arbitrary in the equivalent class x1, and we proved that y is in the equivalent class x2. So we can say that equivalent class x1 is a subset of equivalent class x2. Now the same reasoning we can always show that the equivalent class x2 is a subset of equivalent class x1, and from this we can conclude that the equivalent class x1 and equivalent class x2, they are same. So this discussion demonstrates that there is no real distinction between partitions of a set and equivalent relation in a set. So we prove both things. So now if we start with a partition, we get an equivalent relation by regarding elements as equivalent if they belong to the same partition set, and if we start with an equivalent relation, we get the partition by grouping together or grouping into subsets all elements which are equivalent to one another. So we have a single mathematical idea which we have been considering from two different points of view, and the approach we choose in any particular application depends entirely on our own convenience. In practice, it is almost invariable that case that we use equivalence relations to obtain partitions. Okay. So that means mostly we are given an equivalence relation and we have to find a partition. These partitions may be sometimes very difficult to describe fully, but this equivalence relation, they are somewhat usually easy to define. Now we will discuss some several important examples of equivalence relations. Let I be the set of all integers. Now, if small a and small b and b are elements of this set, we write a equals b, that is, we say a equals b if a and b are the same integer. Now, 2 plus 3 is equals to 5. You know, it's very simple. This means that the expressions on the left and right are simply different ways of writing the same integer. Now, it is apparent that equal, the sign equal, is used in the sense that it is an equivalent relation or equivalence relation in the set capital I. So, this symbol, this equal symbol, is an equivalence relation. Why? The first, a is equals to a for every a, is very evident. Now, second point, a is equals to b, and this implies b is equals to a. It's very obvious. And the third one, a equals to b and b equals to c. They together imply a equals to c. The first property, second, and the third, these three properties together implies that the relation equal is an equivalence relation. So, and it's very obvious that each equivalent set consists of precisely one integer. Now, another familiar example is a set is the relation of equality commonly used in fractions. You can remember that strictly speaking, a fraction is merely a symbol of the form a by b, where a and b are integers and b is not 0. Now consider the fractions 2 by 3 and 4 by 6. Obviously they are not identical, but nevertheless we consider them to be equal. In general, we say that two fractions a by b and c by d, they are equal, and they can be written a by b is equals to c by d if ad equals to ad and bc are equal as integer in the usual sense. This is ad equals to bc. You can readily verify that this relation is an equivalence relation in the set of fractions, and it's very obvious. You can easily do it yourself. And equivalence set of fractions is what we call a rational number. So if we take a rational number, that is half, this is nothing but equivalent set consisting of fractions like 2 by 4, 3 by 6, 4 by 8. This way. Now, everyday users ignores the distinction between fractions and rational numbers. But it is important to recognize the form that strict point of view it is rational number which form part of real number system. Now we are going to another example. This has far more deeper significance, for it provides us basic tools for work of the other sections in the future. For the remainder of this talk, we consider relation between pairs of non-empty sets, and each set mentioned, whether we say explicitly or not, it is assumed to be non-empty. If x and y, capital X and capital Y, are two sets, we say capital X is numerically equivalent to capital Y if there exists a 1-1 or 1-to-1 correspondence between x and y. So we have set capital X, capital Y. We say that set capital X is numerically equivalent to capital Y if there is a 1-to-1 correspondence between x and y. That is 1-to-1 mapping. This relation is reflexive because the identity mapping is always 1-to-1 onto is always symmetric, since if is a function from x to y, it is which is 1-to-1 and onto, then its inverse mapping f inverse is also 1-to-1 onto. It is also transitive. Why? If x f is a mapping from x to y and g is a mapping from y to z, they are 1-to-1 and onto, then the product mapping gf, which is mapping from x to z, is also 1-to-1 onto. Now, numerical equivalence has all the properties of an equivalence relation, and if we consider it as an equivalent relation in the class of all non-empty subsets of some universal set capital U, it groups together into equivalent sets all those subsets of U which have the same number of elements. After we prove the very useful but rather technical theorem, we'll continue with an exploration of the implications of these ideas. The theorem we have in mind is called basically Schroeder-Bernstein theorem, or sometimes Cantor-Schroeder-Bernstein theorem. It says following: we have two sets x and y, capital X and capital Y. They are two sets, they are numerically equivalent. Numerically equivalent means, I have already said, there exists a 1-to-1 correspondence between x and y. So we have two sets x and y, which is they are numerically equivalent to a subset of the others. Then all of x is numerically equivalent to all of y. This is a very interesting theorem. This is Schroeder-Bernstein theorem. It says that we have two sets x and y, and these two sets are numerically equivalent to a subset of the other. Then this theorem said all of set x is numerically equivalent to all of y. We will not go into the proof of this theorem, but it's a very interesting theorem. So rather than going into the proof of this theorem, we will discuss theorem we have previously said, that equivalence theorem, equivalence relation between partition and equivalence relation. We'll do some proper mathematical problem, and we'll show how an equivalence relation makes a partition, and the other way, how we can make an equivalence relation from a partition. We'll discuss via some examples. So in the last two slides, I will discuss, or rather give examples of functions where we have a partition, and from that partition, firstly we'll show an equivalence relation, and in the next example we'll show that if we have a equivalence relation, this equivalence relation will induce a partition. So for the first example, we take the set, a set containing 6 elements, that is 1, 2, 3, 4 and 5. So now we can partition the set such that we take 1, 2, 3, 4, 5 and 6. So we know there are infinite ways of partition, but we have taken this set as our partition set. So we have a set and we have its partition. So our task is to find, or is to develop, the equivalence relation on the set. So the process by which we find this equivalence relation or develop this equivalence relation is like that. We just take the Cartesian product of the first partition with itself, the second partition with itself, and the third partition with itself. So when you take Cartesian product of 1, 2, 3 and 1, 2, 3, we get the set, that is the set containing the ordered pairs 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2 and 3, 3. And when you take Cartesian product of the set 4, 5 with itself, we get the set containing the elements 4, 4, 4, 5, 5, 4 and 5, 5. And lastly, the partition set 6, when you multiply, or when you take Cartesian product with itself, we get the set containing the element 6 and 6. Now we consider the set, containing elements which are actually union of these three sets. So we construct that set 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 3, 2, 3, 3, 4, 4, 4, 5, 5, 4, 5, 5 and 6, 6. So this is eventually a subset of the Cartesian product of original set with itself. So it is a relation. It is very easy, or it is, you can always do it yourself. You can check that this set is actually an equivalence relation. This is actually an equivalence relation of the set 1, 2, 3, 4, 5, 6. So the process is very easy. we have a set, we partition the set, then we take the Cartesian product of each partition set with itself, and we take the union. This is a relation, and this relation is an equivalence relation. This can be very easily proved. So in general, we have a set A, and consider, or let us say that A1, A2, A3 dot dot dot, they as a whole form a partition of the set A. We take the Cartesian product between A1 and the set itself A1, again between A2 and A2, that is Cartesian product between the set A2 with itself, and dot 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 for the others, and we take the union of all these things. So R, we say the relation is R, and R is the union of A1 cross A1, A2 cross A2, and all those others. So this R is an equivalence relation. This can be very easily proved. You can try it yourself. It is your task to prove that this R is an equivalence relation. So the first job is complete. So we have a partition, and we are able to form the equivalence relation from that partition. Next, our task is the reverse way. That is, we have an equivalence relation, and we need to form a partition from that equivalent relation. So for this purpose, let us say A is a set, given set, and f is a function on the set A. So let us consider R is the ordered pair AB such that f of A is equals to f of B. Now this can be very easily, you can do it yourself, that this R is an equivalence relation. So why it is an equivalence relation? Because you can see, or you can do it yourself, that it satisfies the all three properties: reflexive, symmetric, and transitive. It is reflexive because f of A equals to f of A for all A belongs to capital A. It is symmetric because if f of A is equals to f of B, then f of B equals to f of A. And transitive, that is, if f of A is equals to f of B and f of B is equals to f of C, then obviously f A equals to fc. So the set R satisfies all three properties and of to be an equivalence relation. Hence, obviously it is an equivalence relation on A. For a particular example, consider A be the set of integers, that is A equals to Z, and the function f is defined like that: f of x equals to x to the power 4 plus 1. Now if x equals to 0, f of x is equals to 1. Whenever x is plus 1 or minus 1, f of x is equals to 2. Whenever x is plus 2 or minus 2, f of x is equals to 9. Whenever x is plus 3 or minus 3, f of x is equals to 82, and this way. So it's very clear or evident that a partition of Z can be written like that, that is union of those sets. the set containing 0, the set containing -1 plus 1, the set containing -2 plus 2, the set containing -3 plus 3, and this way if we take union of these sets, then is equals to Z. So obviously they are disjoint sets and they form a partition of Z. So in this way, so we start with an equivalence relation and we ultimately got a partition. So we have given the both-sided examples, or we have we have a partition, and from that partition we show how to get the equivalence relation, and reversely we have an equivalence relation, and from that equivalence relation how to get that partition. So this ends the topic of this lecture. We will discuss other things in our next lectures. Thank you.